June 21, 1944. USS Indianapolis, Pacific Fleet flagship anchored at Saipan. Lieutenant Commander Thomas Dyer's hands trembled slightly as he examined the 5-inch shell casing recovered from the previous day's engagement. The fuse housing on the shell's nose, still intact despite firing, looked unlike anything he'd seen in 8 years of naval ordnance inspection. This cannot be a standard mechanical fuse. The housing is completely wrong. The component measured exactly 5.2 inches in length, screwed directly onto the standard 5-inch 38 caliber shell. But where a conventional time fuse showed simple mechanical clockwork, this device featured a rounded nose cap made of an unusual translucent material, something that looked almost like early plastic or bakelite. Through the semi-transparent housing, Dyer could see what appeared to be miniature vacuum tubes, delicate wire coils, and components that belonged in a laboratory radio set, not inside artillery that experienced 20,000 times the force of gravity during firing and spun at 15,000 revolutions per minute. He set the shell down carefully on the workbench. The implications were staggering. If this fuse contained actual radio components, a transmitter and receiver small enough to fit in a 5-inch shell, rugged enough to survive firing, and precise enough to detect aircraft proximity, it would represent a breakthrough in applied physics that shouldn't exist yet. The miniaturization alone seemed impossible. Yesterday's engagement had been remarkable. The Japanese air attack against the Saipan invasion fleet had sent 43 aircraft against the screening destroyers. American ships had shot down 31 before any torpedo bombers reached effective range. The mathematics didn't work. Conventional anti-aircraft fire required an average of 3,000 rounds to destroy a single maneuvering aircraft. Yesterday's engagement had expended only 8,400 rounds, fewer than 300 per kill. Someone had changed the mathematics of aerial combat, and this strange fuse was the answer. The weapon's existence raised immediate questions about American industrial capacity, scientific advancement, and operational security. If the United States could mass-produce miniature radar sets by the thousands, embedding them in consumable ammunition, while keeping the technology completely secret from Japanese intelligence for over 18 months, then the technological gap between the Allied and Axis powers was wider than anyone had publicly acknowledged. What Dyer held in his hands represented the convergence of theoretical physics, industrial engineering, and military necessity. A weapon that turned every 5-inch gun into an intelligent proximity detector, creating kill zones where Japanese aircraft simply exploded before completing their attack runs.
The journey to this revolutionary weapon had begun 4 years earlier, in September 1940. When a group of British scientists arrived in Washington carrying technical specifications for cavity magnetrons, radar systems, and a desperate request. Britain needed American scientific and industrial capacity to develop weapons that might counter the Luftwaffe's bombing campaign. Among the problems presented, conventional anti-aircraft fire was statistically ineffective against high-speed maneuvering aircraft. The National Defense Research Committee assigned the proximity fuse problem to Section T at the Carnegie Institution's Department of Terrestrial Magnetism in Washington. The section's director, physicist Merle Tuve, assembled a team that included electrical engineers, radio specialists, and ordnance experts. Their initial assessment was discouraging. To create a functional proximity fuse, they needed to miniaturize radio transmitting and receiving equipment, technology that currently filled entire rooms, into a package that could fit inside a 5-inch shell, survive the shock of firing, operate reliably in any weather, distinguish aircraft from clouds or ground clutter, and detonate at precise range. Military ordnance officers were skeptical. Previous attempts at proximity fuses had used photoelectric cells or acoustic detectors, both of which proved unreliable in combat conditions. Photoelectric fuses couldn't distinguish aircraft from clouds. Acoustic fuses couldn't function in the noise environment of naval combat. The specification required something entirely new: a miniature radar set with battery power, automatic range detection, and a detonator triggered by radio proximity return. Tuve's team moved to the Applied Physics Laboratory in Silver Spring, Maryland in 1942 as development accelerated. The technical challenges were extraordinary. The vacuum tubes needed to be small enough to fit multiple components inside the fuse housing, yet rugged enough to survive setback forces of 20,000 G during firing. The battery had to be compact, shelf-stable for months, and activate instantly when fired. The transmitter and receiver had to operate at precise frequencies while spinning at 15,000 RPM. The detonator circuit had to distinguish between reflected signals from nearby aircraft versus ground clutter or water surface. By late 1942, the design was complete. The VT Fuze, variable time, a deliberately misleading designation to obscure its true radar function, measured 5.2 inches in length and weighed 2.1 pounds. It contained 5 miniature vacuum tubes manufactured by Raytheon and Sylvania, a battery that activates on firing through inertial force, a transmitter operating at 180 to 220 MHz, a receiver circuit, an amplifier, and a detonator. The entire assembly cost $18 per unit, approximately $350 in current dollars, but represented such advanced miniaturization that British scientists called it the most significant military development of the war outside the Manhattan Project. First combat deployment came on January 5, 1943. USS Helena, a light cruiser screening Guadalcanal's transport area, loaded VT-fused shells in strict secrecy. Gunnery officers received only minimal briefing. The new fuses would improve hit probability against aircraft, recovery of any duds was mandatory, and under no circumstances would VT ammunition be used over land where Japanese forces might recover intact examples. At 13:47 hours, Japanese G-4M Betty bombers approached Henderson Field. Helena's 5-inch batteries engaged at 12,000 yards. The first VT-fused shells detonated at 70-foot proximity to the lead bomber, creating shrapnel patterns that didn't require direct hits. Within 8 minutes, Helena's guns had destroyed 4 aircraft using only 321 rounds, a kill ratio 10 times better than conventional ammunition. The bomber formation broke off without delivering ordnance. Gunnery crews reported hits they knew they hadn't aimed precisely enough to achieve with conventional fuses. The mathematics of anti-aircraft warfare had fundamentally changed.
Through early 1943, VT fuses spread across the Pacific Fleet under strict operational security. Each ship received detailed protocols. VT ammunition was authorized only against aircraft over water. Every unfired round would be accounted for. Beach recovery teams would collect any shells that fell on land. And gunnery officers would not discuss the technology with aircrew or ground forces. The secrecy was absolute. Even downed American pilots captured by Japanese forces couldn't reveal what they didn't know existed. They devastated Japanese air attacks across the Solomon Islands. At Rendezvous Island on June 16, 1943, destroyer USS Pringle engaged 12 Val dive bombers with VT-equipped 5-inch guns. 8 aircraft exploded before reaching effective bomb release altitude. The remaining 4 scattered and missed their targets. Japanese pilots radioed confusion. They reported encountering impossible American anti-aircraft accuracy that seemed to place killing bursts directly in flight paths without requiring direct hits. They protected the Gilbert Islands invasion fleet in November 1943. During the Tarawa landings, screening destroyers created defensive zones where Japanese aircraft simply couldn't penetrate. On November 20, 1943, a coordinated attack by 16 torpedo bombers against transport ships encountered a wall of automatically triggered explosions. 13 aircraft were destroyed before any reached torpedo dropping position. The 3 surviving aircraft released torpedoes wildly from maximum range and retreated. Not a single transport was hit. They transformed the defense of carrier task forces during the Marshall Islands campaign. On February 17, 1944, during strikes against Krakatoa, Japanese retaliatory attacks found American carriers protected by destroyer screens whose 5-inch batteries achieved kill rates that violated every tactical manual's statistical expectations. Rear Admiral Mark Mitcher reported that VT-equipped destroyers were destroying attacking aircraft at 3 times the rate of ships using conventional ammunition, a capability that fundamentally altered carrier task force defensive doctrine. The Japanese noticed the pattern. Intelligence reports from surviving pilots described American ships with extraordinary anti-aircraft capability, but could not identify the mechanism. Some pilots theorized the Americans had developed new gun-laying radar with impossible accuracy. Others suggested new shell types with larger bursting charges. None understood the actual technology. Commander Minoru Genda, perhaps the Imperial Japanese Navy's finest aviation tactician, reviewed action reports throughout 1943 and noted, "American defensive effectiveness against air attack has increased substantially beyond what improved gunnery training or radar fire control should achieve. We must assume a technological factor we have not identified." The effectiveness depended entirely on maintaining operational security. If Japanese technical intelligence recovered even one intact VT fuse, they might duplicate the technology or develop countermeasures. American operational orders were explicit. VT ammunition would never be used over land until Japan's industrial capacity was destroyed. Every ship maintained recovery protocols. Beach parties combed shorelines after engagements. The technological advantage existed only as long as the technology remained secret. And through all of 1943, despite tens of thousands of VT shells fired in combat, not a single intact fuse fell into Japanese hands. But the weapon's true test came in June 1944, when the Imperial Japanese Navy committed its remaining carrier aviation strength to stopping the American drive toward the Philippines. The Battle of the Philippine Sea would demonstrate exactly what VT fuses could accomplish against mass aircraft attack, and prove to Japanese commanders that something fundamental had changed in the mathematics of naval air combat. June 19, 1944, 1,000 hours. Approximately 200 miles west of Guam. The largest carrier battle of the Pacific War began when American radar pickets detected the first wave of Japanese aircraft approaching Task Force 58. Vice Admiral Mark Mitcher's 15 carriers and 7 battleships maintained combat air patrol using fighters. But the outer defensive ring consisted of VT-equipped destroyers, whose 5-inch batteries would engage any aircraft penetrating the fighter screen. The Japanese strike force consisted of 373 aircraft, the entire remaining carrier aviation strength of the mobile fleet. Their mission? Destroy enough American carriers to force a negotiated settlement before American industrial superiority rendered continued resistance impossible. Japanese air commanders planned to overwhelm American fighter defenses through coordinated mass attack, then press home torpedo and bomb runs using the skill that had devastated Allied fleets in 1941-42. They expected casualties. They did not expect what happened. The first wave of 69 aircraft encountered American fighters 40 miles from the task force. The Hellcats shot down 25 before the Japanese reached the screening destroyers. Then, the remaining aircraft entered the range of 5-inch guns and began exploding without apparent cause. Lieutenant Junior Grade Zenji Abe, flying a B-6N JIL torpedo bomber, later reported, "The American anti-aircraft fire seemed to follow us precisely. Explosions appeared directly in our formation without any visible shell missing and bursting elsewhere. It was as if they were detonating the shells by magic at the worst possible position for our aircraft." They weren't missing. The VT fuses were working exactly as designed. Each 5-inch shell transmitted a radio signal and monitored the returned echo. When the signal reflected from metal at approximately 70 feet distance, the fuse detonated the shell automatically. The shrapnel pattern from a single 5-inch shell at 70-foot range covered sufficient volume to damage any aircraft within that radius. Gunnery crews didn't need direct hits. They needed proximity. The Japanese pilots interpreted the kill pattern as impossible marksmanship. They couldn't conceive that the shells themselves were intelligent. USS Alabama, steaming as part of the battleship screen, engaged the second wave at 11:23 hours. Her 5-inch batteries fired 352 rounds in 18 minutes and destroyed 11 aircraft, an average of 32 rounds per kill. Conventional ammunition typically required 1,200 rounds per aircraft destroyed. The gunnery officer, Lieutenant Commander Paul Smith, wrote in his action report, "The new ammunition performs beyond any statistical expectation. Gun crews are reporting hits they know they did not aim accurately enough to achieve. Recommend immediate expansion of distribution to entire fleet." By 14:30 hours, when the fourth and final Japanese wave withdrew, American ships had shot down 116 aircraft using VT-equipped 5-inch guns. The total ammunition expenditure was approximately 35,000 rounds, an average of 302 rounds per kilo. Fighter aircraft accounted for an additional 234 destroyed. Of the 373 Japanese aircraft launched, only 130 returned to their carriers. Not a single American ship was significantly damaged. Japanese pilots called it flying through fire islands. They reported that American destroyers created walls of explosions that made coordinated attack impossible. What the Japanese pilots didn't understand, what they couldn't understand without examining an intact fuse, was that every American shell carried a miniature radar set that transformed the 5-inch gun from a ballistic weapon requiring direct hits into a proximity-triggered area denial system. The technology represented such a fundamental shift in anti-aircraft warfare that Japanese tactical doctrine based on maneuvering to avoid aimed fire was obsolete. No amount of pilot skill could evade weapons that exploded automatically at proximity. After the battle, Japanese carrier commanders attempted to understand what had changed. Intelligence reports noted substantial improvement in American anti-aircraft effectiveness, but attributed it to better radar fire control, improved gunnery training, or new shell designs with enhanced fragmentation. Some reports speculated about acoustic or magnetic fuses, but these theories couldn't explain the consistent 70-foot burst altitude that pilots reported. The actual mechanism, radio proximity detection, never appeared in Japanese intelligence assessments because it seemed technologically implausible. How could Americans build miniature radio sets rugged enough to survive being fired from guns, cheap enough to expend by the thousands, and reliable enough to detonate consistently at precise range? The answer was American industrial capacity combined with absolute operational security.
By June 1944, manufacturing facilities at Eastman Kodak, Sylvania, and Raytheon were producing 40,000 VT fuses daily. Each fuse underwent individual testing before shipment. Quality control rejected any unit that failed to meet specifications. The industrial process that made mass production possible, assembly line manufacture of miniature vacuum tubes, automated battery insertion, precision calibration of transmitter frequency, represented manufacturing capability that Japan simply did not possess. Even if Japanese engineers had captured an intact VT fuse and understood its operation, they lacked the industrial infrastructure to replicate it. Commander Minoru Genda spent the remainder of 1944 analyzing action reports from Philippine Sea and subsequent engagements. His assessment, written in November 1944, concluded, "American anti-aircraft capability has reached levels that make traditional torpedo attack profiles suicidal. We must assume they possess either substantially improved proximity detection or a shell type we have not identified. Regardless of mechanism, the tactical reality is clear. Our aircraft cannot approach American ships in sufficient numbers to achieve decisive results. The mathematics of attrition have shifted irreversibly against us." He was correct. The mathematics had changed. What he didn't know was that the change came not from improved skill or better tactics, but from a weapon that transformed every American 5-inch gun into an automated proximity detector. A weapon whose development had begun with one physicist ignoring direct orders to abandon an impossible project, and whose secrecy was maintained through industrial security measures that kept Japan ignorant of the technology until the war's end. The VT fuse existed because Merle Tuve refused to accept that the problem was impossible. In October 1940, when the National Defense Research Committee assigned Section T to develop a proximity fuse, most ordnance experts considered radio-based designs impractical. The requirements seemed incompatible with physical reality. Create a miniature radio transmitter and receiver that fits inside a 5-inch shell, survives setback forces of 20,000 G during firing, operates while spinning at 15,000 RPM, distinguishes aircraft from ground clutter, detonates at 70-foot proximity with 95% reliability, costs less than $20 per unit, and requires no external power source. The strategic context drove urgency. Britain was losing the air war. Luftwaffe bombers were devastating British cities, and conventional anti-aircraft fire was statistically ineffective. Pre-war estimates suggested that shooting down a single bomber required 2,500 shells on average. If Britain could develop proximity fuses that reduced ammunition requirements by even 50%, the economic and tactical advantages would be substantial. American industrial capacity could mass produce such weapons, but first, someone needed to prove the concept was feasible. Tuve assembled a team of specialists, electrical engineers from Bell Laboratories who understood radio miniaturization, ordnance experts from the Naval Proving Ground who knew what forces shells experienced during firing, and physicists who could calculate the radio wave propagation necessary for proximity detection. Their first prototypes failed catastrophically. Vacuum tubes shattered during firing. Batteries leaked. Transmitter circuits couldn't maintain frequency calibration while spinning. Detonators triggered prematurely or failed to trigger at all. The breakthrough came from accepting that every component needed complete redesign. Commercial vacuum tubes were too fragile, so they developed reinforced tubes with heavy filaments and shock-mounted internal elements. Standard batteries couldn't survive setback forces, so they designed a battery that used firing acceleration to force electrolyte into position,
activating only after leaving the gun barrel. Conventional transmitter circuits couldn't operate while spinning, so they created a simple oscillator design with minimal components that maintained frequency despite rotation. The mathematics were brutally simple. To detect an aircraft at 70 feet, the transmitter needed to broadcast at 180 to 220 megahertz. Frequencies where the wavelength was short enough for proximity detection but long enough to avoid excessive atmospheric absorption. The receiver needed to distinguish between the transmitted signal and the reflected echo, which required an amplifier circuit sensitive enough to detect signals reflected from metal at 70 feet, but not so sensitive that it triggered from ground clutter at longer ranges. The entire circuit needed to operate for only 20 to 30 seconds, the shell's flight time from firing to impact, which simplified battery requirements but demanded instant activation and stable operation under extreme acceleration and rotation. These two requirements, miniaturization and ruggedization, existed in direct opposition. Smaller components were more fragile. More robust components were larger. Each cubic centimeter inside the fuse housing represented engineering compromises between competing requirements: battery capacity versus weight, transmitter power versus component size, receiver sensitivity versus false trigger probability, detonator reliability versus safety during handling. The decision that defined the VT Fuze success was prioritizing reliability over sophistication. Early designs attempted complex frequency-modulated transmitters that could distinguish aircraft altitude and velocity. Tuve's team abandoned these approaches. The final design used the simplest possible circuit: a fixed-frequency transmitter, a receiver tuned to the same frequency, an amplifier, and a threshold detector that triggered the detonator when signal strength exceeded a specific value. No frequency modulation, no velocity measurement, no altitude discrimination. Just proximity detection at 70 feet with 95% reliability. This simplification made mass production feasible. By eliminating complex circuits, the design used only 5 vacuum tubes instead of 8 or 10. Fewer components meant higher reliability, faster assembly, and lower cost. The trade-off was reduced capability. The VT Fuze couldn't distinguish between aircraft flying toward the ship versus aircraft flying parallel to the trajectory. It simply detonated whenever metal reflected sufficient signal at 70-foot range. For anti-aircraft use over water, this limitation didn't matter. Every aircraft within 70 feet represented a valid target. The justification for these design choices seemed obvious in retrospect, but required courage in 1941. Military procurement officers wanted sophisticated weapons with multiple capabilities and fail-safe redundancy. Tuve's team delivered a weapon that did exactly one thing: detect proximity to metal and detonate. But did that one thing with extraordinarily reliability under conditions that destroyed more complex systems. They accepted that simplicity was strength. They understood that a weapon that worked adequately in 95% of combat conditions was infinitely more valuable than a weapon that worked perfectly in laboratory conditions but failed under combat stress. By January 1942, prototypes were functioning reliably in testing. By August 1942, Eastman Kodak, Sylvania, and Raytheon had established production lines. By December 1942, the first VT fuses reached Pacific Fleet ships under security protocols that prohibited even acknowledging their existence. The weapon that military experts had called impossible in 1940 was entering mass production 2 years later, a testament to focused engineering, industrial capability, and absolute commitment to a single design philosophy: create the simplest weapon that solves the problem, then manufacture it by the millions.
The VT Fuze's devastating effectiveness became apparent throughout 1944 as Japanese air attacks encountered consistently lethal defensive fire. What pilots interpreted as impossible American gunnery accuracy was actually mathematical certainty. When shells automatically detonated at 70-foot proximity, aircraft couldn't evade by maneuvering, because evasion required maintaining distance from shells that exploded before missing their targets. February 17–18, 1944, during carrier strikes against Truk Atoll, demonstrated the weapon's tactical dominance. Japanese air commanders launched 73 aircraft in retaliatory attacks against Task Force 58. American Combat Air Patrol destroyed 28 before the remaining 45 reached the screening destroyers. VT-equipped 5-inch guns engaged at maximum range. The battle report from USS Bunker Hill recorded the pattern. Aircraft approaching in attack formation encountered defensive fire at 12,000 yards. Multiple aircraft observed exploding before reaching effective torpedo range. Coordinated attack dissolved into individual aircraft attempting evasion. Only 3 aircraft reached within 5,000 yards of formation center. All 3 destroyed by close-end defensive fire. No ships damaged. The mathematics of attrition accumulated relentlessly. On March 30, 1944, during strikes against Palau, Japanese defenders launched 46 aircraft. 17 destroyed by fighters. 21 destroyed by VT-equipped ships firing 5,837 rounds, an average of 278 rounds per kill. 8 aircraft retreated without attacking. No American ships hit. On April 29, 1944, during strikes against Truk, 32 Japanese aircraft attacked. 11 destroyed by fighters. 16 destroyed by shipboard anti-aircraft fire using 4,250 rounds, 266 rounds per kill. 5 aircraft withdrew. No damage to American ships. Lieutenant Sadamu Kamachi, a B-6N torpedo bomber pilot who survived 4 missions against American task forces between March and July 1944, wrote in his diary, "Approaching American ships has become suicide. Their anti-aircraft fire creates a wall that cannot be penetrated. Aircraft explode before reaching attack position. Those that survive cannot maintain formation. Pilots are focused entirely on evasion rather than coordinated attack. We cannot win this way. They have changed the rules of engagement and we have no counter." Japanese naval aviation attempted modifications. Beginning in April 1944, some units adopted ultra-low-level approach profiles, flying at 50 feet above the ocean to reduce radar detection and force American gunners to fire at depression angles where radar ranging was less effective. The tactic failed. VT Fuses detected aircraft at 70 feet regardless of altitude or approach angle. Low-altitude approaches simply allowed ships to engage at closer range with shorter time of flight, increasing hit probability. Other units attempted high-altitude dive attacks, believing that steeper attack angles might confuse American fire control. This tactic also failed. VT Fuses detonated at 70-foot proximity regardless of aircraft altitude or attack geometry. The only difference was that dive attacks allowed longer engagement time, giving 5-inch batteries multiple firing opportunities as aircraft descend through maximum range toward their targets. By June 1944, as demonstrated during the Battle of the Philippine Sea, Japanese tactical aviation was operationally defeated. Not by superior American fighter aircraft, though the F-6F Hellcat was excellent. Not by better trained American pilots, though training advantages were substantial, but by a weapon that transformed statistical probability into virtual certainty. If an aircraft entered the engagement envelope of VT-equipped 5-inch guns, it would likely be destroyed. Period. No amount of maneuvering or courage could overcome weapons that exploded automatically at proximity. The pattern continued through late 1944 and into 1945 as Japan adopted kamikaze tactics. Suicide attacks represented Japan's final adaptation. If aircraft couldn't survive long enough to release weapons and return, then aircraft themselves would become weapons. Kamikaze attacks eliminated the need for skilled pilots to survive long enough to develop expertise. Every pilot became expendable after one mission. VT fuses made kamikaze attacks marginally more difficult, but not impossible. The tactics shifted the engagement. Instead of coordinated torpedo attacks requiring multiple aircraft maintaining formation through defensive fire, kamikaze operations sent individual aircraft diving directly at ships from various altitudes and angles.
VT fuses still destroyed most attackers, but determined pilots diving from multiple vectors occasionally penetrated defensive fire through sheer numbers. April 6, 1945, the first massive kamikaze attack against the Okinawa radar picket line demonstrated both the VT fuse's capability and its limitations when facing mass suicide attacks. USS Bush, stationed on Radar Picket Station 1, faced approximately 150 Japanese aircraft throughout the day. Her 5-inch batteries fired continuously for 2 hours, expending 1,847 VT-fused shells and destroying 22 confirmed aircraft. The ship's action report noted, "Defensive fire maintained maximum rate. Aircraft destroyed at ranges from 8,000 yards to point blank. VT ammunition performed as designed. However, volume of attacks exceeded defensive capability. Multiple simultaneous diving attacks from various vectors cannot all be engaged before impact." Bush was struck by 3 kamikaze aircraft within 15 minutes and sank with casualties of 94 crew killed. But her sister ship, USS Calhoun, also on radar picket duty and similarly equipped with VT ammunition, engaged 68 aircraft and destroyed 15 before being struck by 2 kamikazes and sunk. Between both ships, they destroyed 37 attacking aircraft using approximately 3,200 rounds, an average of 86 rounds per kill, the most efficient anti-aircraft kill ratio recorded in naval history. Japanese pilots who survived kamikaze missions, those whose aircraft were too damaged to complete attacks and who managed emergency landings, reported consistent experiences. Petty Officer Hachiro Hosokawa, whose Zero was damaged during an attack on radar picket destroyers in April 1945, described the defensive fire. "The explosions appeared everywhere, not random bursts, precise detonations directly in our flight paths. Some pilots believed the Americans could predict where we would fly. I think they simply filled the sky with explosions and we flew into them. There was no way to avoid it. Every time aircraft approached, shells exploded. The only survivors were those lucky enough to find gaps in the fire, and there were very few gaps." He was describing exactly what VT fuses were designed to accomplish: fill the defensive envelope with automatically triggered explosions positioned precisely where aircraft flew. No marksmanship required. No predictions necessary. Just physics. Radio waves reflected from metal, triggering shells to detonate at the worst possible location for any aircraft within proximity. The weapon that Merle Tuve had developed despite being told it was impossible, that had been manufactured by the millions while remaining completely secret, that Japanese intelligence never understood despite encountering it hundreds of times, had transformed naval air defense from a statistical improbability into virtual certainty. By 1945, approaching American ships equipped with VT fuses meant flying into automated kill zones where survival depended entirely on overwhelming defensive fire through sheer numbers, a tactical approach that cost Japan thousands of aircraft and pilots without achieving strategic objectives. Between January 1943 and August 1945, American industry manufactured approximately 22 million VT proximity fuses.
Production centered at three primary facilities: Eastman Kodak in Rochester, New York, Sylvania Electric in Emporium, Pennsylvania, and Raytheon Manufacturing in Waltham, Massachusetts. Each facility operated under security protocols that prohibited workers from knowing the fuse's ultimate purpose. Assembly line workers manufactured components without understanding how they functioned together. Only final assembly technicians saw complete fuses, and even they received no information about combat effectiveness or tactical employment. The standard Mark 32 VT Fuze equipped 5-inch 38 caliber naval guns, the primary anti-aircraft weapon aboard American destroyers, cruisers, and battleships. The Mark 53 variant equipped 3-inch 50 caliber guns on smaller vessels. Later variants included the Mark 176 for 40mm Bofors automatic guns, though these saw limited deployment before war's end. Each fuse cost $18 to manufacture in 1943 dollars, approximately $350 today. But reduced ammunition expenditure required to destroy aircraft from an average of 2,500 rounds to approximately 300 rounds. The economic calculation was brutally simple. Spending $350 per fuse saved firing 2,200 rounds that cost significantly more to manufacture and transport to forward areas. Distribution followed strict protocols. VT ammunition remained under constant security. Ships logged every round issued and every round expended. Beach recovery teams operated throughout the Pacific Theater, collecting any VT fused shells that landed on islands or reefs. The U.S. Navy's absolute prohibition against using VT ammunition over land, maintained until August 1945, ensured that no intact fuses fell into Japanese hands even if shells failed to detonate. This operational security proved so effective that Japan never captured a functional VT fuse during the war. Loss rates for VT-equipped shells were remarkably low. Approximately 99.2% of VT fuses detonated as designed. The 0.8% failure rate resulted primarily from manufacturing defects caught during final testing, damage during transport, or premature detonation caused by electrical interference. Combat commanders reported that VT ammunition was more reliable than conventional time fuses, which required manual setting before firing and frequently malfunctioned due to incorrect timing calculations or mechanical failure. Crew casualties aboard ships equipped with VT ammunition were substantially lower than those aboard ships using conventional ammunition. While comprehensive comparative statistics are difficult to compile due to numerous variables affecting survivability, action reports from Task Force 58 operations in 1944 show that ships equipped with 75% or more VT ammunition in their magazines suffered 40% fewer casualties from successful air attacks compared to ships with 25% or less VT ammunition. The correlation strongly suggests that VT fuses prevented aircraft from reaching effective attack positions, reducing the number of successful torpedo and bomb hits. Survivors consistently testified to the weapon's psychological impact on attackers. Rear Admiral Willis Lee, commander of Battleship Division 6, wrote in September 1944, "Japanese pilots have changed their approach patterns substantially since we deployed VT ammunition. They no longer maintain tight formations during final attack runs. Instead, they spread out and attempt individual evasive approaches. This behavioral change indicates they recognize our increased defensive effectiveness, though we have no intelligence suggesting they understand the mechanism. Whatever they believe we've done, they fear it." Captain Arleigh Burke, commanding Destroyer Squadron 23, reported similar observations after engagements off Bougainville in November 1943.
enemy aircraft are maintaining greater standoff distances than previously observed. Torpedo bombers that formerly pressed attacks to 1,000-yard range now release torpedoes from 3,000 yards and immediately evade. This substantially reduces their hit probability. We attribute this behavioral change to recognition of improved defensive fire effectiveness, though we emphasize that crews have not been informed of the specific mechanism. The comparative analysis with Japanese anti-aircraft capability reveals stark technological disparity. Japanese ships equipped with 5-inch 40-caliber guns used conventional time or contact fuses throughout the war. These required manual range estimation, time setting, and direct hits to destroy aircraft.
Japanese anti-aircraft effectiveness remained essentially unchanged from 1942 through 1945, with average ammunition expenditure of approximately 2,800 rounds per aircraft destroyed. American ships using VT fuses averaged 300 rounds per aircraft destroyed, a 9-fold improvement in efficiency. This efficiency gap derived from fundamental design philosophy differences. Japanese ordnance development prioritized offensive capability, longer-range guns, heavier shells, higher explosive content, at the expense of defensive innovation. American ordnance development after 1940 increasingly emphasized defensive systems, recognizing that protecting platforms, ships, aircraft, ground installations was as strategically important as destroying enemy platforms. The VT fuse exemplified this philosophy. It didn't increase the destructive power of 5-inch shells, but it increased their probability of detonating near targets by an order of magnitude. The philosophical difference extended beyond weapons design to broader strategic vision. America protected its trained personnel because training required years and combat experience was invaluable. Japan accepted higher casualty rates among skilled personnel because cultural values emphasized mission accomplishment over individual survival. By 1945, this philosophical difference had produced measurable outcomes. American ships operated with increasingly experienced crews who survived multiple engagements, while Japanese ships operated with increasingly inexperienced crews replacing those lost in previous battles. The VT fuse contributed directly to this disparity by ensuring that American ships survived air attacks that would have caused severe casualties with conventional defensive fire. The weapon's true strategic value wasn't measured in aircraft destroyed or ammunition saved, but in missions accomplished without loss. Every carrier strike that returned intact, every amphibious assault that landed troops without losing transports to air attack, every resupply convoy that reached forward bases without losses. These outcomes derived partially from the invisible advantage of VT fuses creating defensive zones where Japanese aircraft simply couldn't penetrate. The weapon worked because it was secret, effective, and mass-produced at scale only American industry could achieve.
June 21, 1944. USS Indianapolis. Lieutenant Commander Thomas Dyer set the VT-fused shell carefully back on the workbench and drafted his preliminary report. The examination confirmed what the previous day's engagement statistics had suggested. American naval ordnance had achieved a breakthrough that Japanese technical intelligence hadn't detected despite 18 months of combat exposure. The weapon in front of him represented the convergence of theoretical physics, industrial manufacturing, and operational security, a technological advantage maintained through absolute secrecy and enforced through recovery protocols that prevented enemy examination. The VT Proximity Fuze's connection to Japan's eventual surrender was indirect but significant. The weapon didn't win the war by itself. No single weapon did. but it fundamentally altered the tactical balance of naval air combat at precisely the moment when Japan's carrier aviation was attempting its final offensive operations. The Battle of the Philippine Sea in June 1944, where VT-equipped ships destroyed 116 Japanese aircraft, effectively eliminated Japan's naval aviation as an offensive force. Without effective carrier aviation, Japan couldn't contest American advance through the Central Pacific. Without contesting that advance, Japan couldn't prevent American capture of bases within B-29 range of the home islands. Without preventing that, Japan couldn't avoid strategic bombing and eventual defeat. The final irony was mathematical. Japan entered World War II with the world's most skilled naval aviators, the longest-range torpedo bombers, and tactical doctrines proven effective against the British and Americans in 1941-42. By 1944, those advantages were irrelevant. American ships equipped with weapons that automatically detected proximity and detonated without requiring direct hits had rendered traditional torpedo attack profiles suicidal. No amount of courage, skill, or tactical innovation could overcome physics. Radio waves reflecting from aircraft metal triggered shells to explode at 70 feet, creating lethal shrapnel patterns that required only proximity, not precision. The lesson from the VT fuse extends beyond World War II's specific tactical situation. It demonstrates that breakthrough technology, properly secured and mass-produced, creates asymmetric advantages that enemy adaptation cannot counter when enemies don't understand the mechanism they're attempting to counter. Japanese pilots changed tactics repeatedly throughout 1943-44, trying low-altitude approaches, high-altitude dives, dispersed formations, and finally kamikaze tactics. Every adaptation failed because none addressed the actual problem. Their aircraft reflected radio signals that triggered automatic detonation at fixed proximity. They were adapting to a weapon they couldn't see, understand, or counter. The broader implications remain relevant to contemporary military technology development. The VT fuse proved that the side willing to invest in revolutionary rather than incremental improvements and willing to maintain operational security absolutely can shift the fundamental mathematics of combat. The weapon didn't make American gunners more accurate. It made accuracy irrelevant. That conceptual leap from trying to hit targets to creating zones where targets destroy themselves represents the kind of paradigm shift that changes warfare permanently. Merle Tuve's decision in 1940 to continue developing a weapon that senior military officers called impossible, combined with American industry's capacity to manufacture 22 million units while maintaining complete secrecy, created a weapon that killed an estimated 70% of Japanese aircraft engaged by VT-equipped ships. Vice Admiral Richmond Kelly Turner's assessment, calling it the single most important new weapon of the war outside atomic weapons, was statistically justified. More Japanese aircraft were destroyed by VT fuses than by any other single American weapon system, and those aircraft were destroyed before they could inflict damage on American ships and crews. The examination of that VT fuse shell aboard USS Indianapolis on June 21, 1944, provided confirmation of what combat statistics had already demonstrated. America had changed the rules of naval air combat, and Japan never understood what rules had changed. The weapon that British scientists called the most significant military development of the war outside the Manhattan Project had transformed defensive anti-aircraft fire from a statistical improbability to virtual certainty. The Japanese naval aviation, which had devastated Pearl Harbor, sunk HMS Prince of Wales and Repulse, and dominated the Pacific in 1941-42, was tactically defeated by 1944, not by superior enemy pilots, but by superior enemy physics. The VT Proximity Fuze was not poorly designed. It was brilliantly designed to achieve specific goals: detect aircraft proximity, detonate automatically, survive firing forces, operate reliably in combat conditions, and cost little enough to manufacture by the millions. Those goals explicitly included making enemy approach to American ships suicidal, while maintaining such absolute secrecy that enemies couldn't develop countermeasures. And in accomplishing those goals completely, the VT Fuze demonstrated a principle that remains valid today. The side that creates breakthrough technology, secures it absolutely, and manufactures it at scale wins not just battles, but entire campaigns. Because revolutionary weapons change the mathematics of warfare itself, and mathematics cannot be defeated by courage alone.